Okay, so I think we can start again. So we're very happy to have Camille Cazaux speaking, and yeah, please, you have the stage, Camille. Okay.
So thank you very much to the invitation, for the invitation, sorry. It's a great pleasure for me to present some aspects of my work, and this work is being conducted in collaboration with my PhD supervisors, Anna Benamou and Nicolas Boupin. And today I will discuss the limiting degree distribution for a sublinear preferential attachment model with communities. Since this is a mathematics and physics seminar, I will try to be as clear as possible. And,
yeah, the math are online, so.
And to be comprehensible by everyone, regardless of the background, the scientific background of everyone. And first of all, I would like to explain this title and to do so, to give some motivations for studying this question. So part one, motivations. And historical model. So we know that large complex networks appear everywhere around us, from technological systems such as the World Wide Web. To biological networks, to social or information networks. And in many examples, empirical data show that the degree distribution, the limiting degree distribution, follows a poor law. In other words, while most vertices have only a few connections, a small number of vertices act as highly connected hubs. And classical random graph models such as the Albert-László model fail to reproduce this behavior. They produce graphs whose degrees concentrate around a typical scale, and thus cannot capture the e-details observed in data. Okay. And yes, I forgot to say something. Is that whereas degrees concentrate around a typical scale in the Albert-László model, for instance, a poor law degree distribution is said to be scale-free. So it's very different. And this discrepancy motivated the search for a generative model capable of producing poor law degree distribution. Which means that a poor law degree distribution is a law such that the probability that the degree of a vertex V, so the degree to be equal to K, is proportional to K at the minus alpha, where alpha is typically a parameter between 2 and 3. It's necessary to have a summable function, you see, in order to be able to normalize, in order to have a probability measure. Okay, and in 1999.
So this is the behavior for the Albert-László model, or this is the other one?
This is the other one.
The other one, okay.
Because the Albert-László model doesn't have a poor law distribution. This is a poor law distribution. Which is scale-free. Okay. And in 1999, 1999, physicists Barabási and Albert. Barabási and Albert. Introduced the preferential attachment mechanism as a simple and universal explanation for the emergence of such poor law distribution. And the key idea is straightforward. New vertices are more likely to connect to already well-connected vertices. And this is very natural if you think, for instance, about social networks. This mechanism is said to be a self-reinforcing mechanism, which creates naturally ups and leads to a degree distribution with poor law tail. More formally, the preferential attachment model can be defined as follow. So definition. Preferential attachment model. Let G0 be a finite connected graph. Finite connected graph. And we construct a graph process indexed by n, the set of the integers. Suppose that Gn, the graph at time n, has already been constructed. Then at time n plus 1, v n plus 1, a new vertex arrives and attaches to the graph Gn to a vertex attaches to V, a vertex of Gn, according to the following probability. According to the following probabilities, so the probability that V n plus 1 attaches to V given the sigma algebra Fn is equal to the degree of V divided by, in order to have a probability, divided by the degree of U, where U are the vertices of Vn. And Fn is the sigma algebra generated by G0, G1, Gn. So it is the entire history of the process. Okay. I recently stated that this model makes it possible to obtain a poor law degree distribution. So the question is why? And as an easy exercise, I suggest that we prove this result, which will allow us to see why it is true, why we have such a limiting degree distribution, and we will see what arguments are typically used. It's a good introduction to the methods. But an easy introduction, but still interesting. Okay. So proposition. Preferential attachment model. Exhibit. for a low degree distribution. So the idea is to if I set P n P d n, let P d n be the proportion of vertices of degree d at time n. Our goal is to determine the limit when n goes to infinity of the quantity PDN for all d. Okay, and let's Q dn be n plus 1 times P dn. Yes, I forgot to say that I consider that that G0 consists in a single vertex, so it is the root of the process, and so G1, G2, etc. So at time 0 we have one vertex, at time 1 we have two vertices, and so at time n we have n plus 1 vertices. So QDN is exactly the number of vertices of degree d at time n. And we can obtain a recurrence relation for this sequence. So let's take the expectation of the Q z n plus 1 given Fn. Okay. So the expected number of vertices of vertices of degree d at time n plus 1 is the number of vertices of degree d at time n minus the expectation of the indicator that there exists a vertex v in Gn such that v n plus 1 attaches to v and the degree of v is equal to d, because in g n plus 1, if v is of degree d, then its degree becomes d plus 1. So we have to remove 1, plus the expectation of the indicator that there exists v in v gn such that v n plus 1 attaches to v and the degree of v equal d minus 1. Okay. And we have to add 1 if d equal 1. Because if d equal 1, we add a vertex of degree 1. Okay. So it's a basic relation. And then we can observe that the expectation of the indicator is the probability that there exists V in VGN, etc. So this is the sum over all V in VGN of the probability that V and the degree of V in Gn is equal to V, probably that Vn plus 1 attaches to V plus the sum, the same sum, but when the degree of V is equal to V minus 1, minus delta V1. Okay, and this probability, we know the value of this probability because I forgot. Okay. And this probability is equal to the degree of V, degree of V, but the degree of V is D over the sum of the degree of U, or when U is a vertex of Gn. And we know the number of we know the value of this term, in fact, because we have in G0 we have just one vertex, so this sum is equal to 0. In G1, two vertex, and the sum of the degree is 1 plus 1 equal to 2. In G2, we have these 3, and we have the sum of the degree is 1, 2, 3, 4. Okay, G3, we have can have different trees, but imagine we have these 3. The sum of the degree is the degrees is 1, 2, 6. Okay, yeah. And in Gn, the sum is 2 times n. So this term is d over 2n, and we do the same thing here, and we have d minus 1 over 2n. Okay. Okay. So we have the expectation of QD n plus 1 given Fn is equal to, at the end, we do some computation, at the end is equal to QD n 1 minus d over 2n plus 1 over 2n d minus 1 q d minus 1 n plus delta d. Okay, and by a simple computation, we obtain a recursion for the sequence PDN, and we have this relation. So now we need to solve this recurrence relation. Note that the recurrence relation for degree d also depends on the degree d minus 1. And this suggests that we start by determining the limit when d is equal to 1, and then we move on to degree 2 and so on. And to do so, we are going to use a very useful lemma, which can be found in a experimental survey titled "A Survey of Random Processes with Reinforcement." This lemma states that if an and bn are two sequences of random variables, of positive random variables, positive random variables, and then psi n and Rn, two sequences of real random variables, and A and kappa, two strictly positive constants, such that one, for all n in n star, we have b n plus 1 minus b n equal to 1 over n, a n minus kappa bn plus psi n plus 1 plus r n. 2 an converges almost surely towards a when n goes to infinity. 3, the sum of the Rn is finite almost surely. And 4, the expectation of psi n plus 1 given Fn is equal to 0, and the sequence Cn is bounded in L2, so the supremum of the expectation of Cn squared is finite. So if we under this fourth statement, this four assumption, then we have n converges almost surely when n goes to infinity towards a divided by kappa. Okay. So we in order to solve the recursion, we just have to apply a dilemma and to do the good identifications. Okay, so we start by the degree d equal to 1. And for d equals to 1, the recursion becomes the expectation that P1 n plus 1 given n minus 1n is equal to the following. So if we set Bn equal to P1n, kappa equal to 1 plus 1 half, and then an equal to a equal to 1, psi n plus 1 equal to n plus 2 times b n plus 1 minus expectation of bn plus 1 given fn. And Rn equal to the big O n to the minus 2. Then, thus, we have bn plus 1, then bn plus 1 minus bn equal to we can check that we have the 4 assumption in this context, and then we by applying the lemma we obtain that Vn P1n converges when n goes to infinity towards 1 over 1 plus 1. And we do the same for the degree 2, etc. And we can guess the general form of the general case. And the general case is when d is but an integer, and so by induction, we obtain for all in n star that the proportion of vertices of degree d tends to almost surely 1 over 1 plus d over 2 times the product and you can simplify this expression to have 4 over d plus 1 d plus 2 and is equivalent when d tends to infinity. Okay. So
Just
this,
one clarifying question.
Yes.
Sorry. This order n to the -2 terms, in principle, these are terms that you know, but you don't need them to actually find the eventual expression, or are these terms that are unknown? Or?
yes, we know these terms, but I don't do. I didn't write the details
No,
of
sure,
the
yeah,
of
yeah,
the
okay.
of the expression, but it's very easy to write it, and
Okay, it's just you don't need it in this.
and because we have these results, and of course the sum of n to the -2 is finite, so it doesn't matter in the limit, so
Yeah.
we can.
Yes.
Okay, and so this is not exactly a power law, but it is a power law in an asymptotic sense. Okay, and so it is an easy proof, and this proof doesn't require many ideas. It's just a recursion and the application of a lemma. The lemma is not so trivial, but we just used a few ingredients, but a central tool remains this lemma that is a lemma of stochastic approximation approach, and I will discuss more later this lemma. Now let's return to the title of the talk, and so far I have discussed preferential attachment, but up to this point there are still no communities, and I haven't said anything about the term sublinear either. First of all, I will introduce a variant of this model with communities, and only later we will get to what is called a sublinear model. So part 2. Part 2, preferential attachment with communities. And for this part, I refer to a 2013 paper by Jonathan Jordan titled Geometric Preferential Attachment in Non-Uniform Metric Spaces. Okay, the difference from the previous model is that each new node is randomly assigned to a community according to a distribution mu. And if, for instance, there are n communities, mu is a probability measure over the set 1, n. So, for instance, mu I is the expected number of vertices of the community I in the graph process. Then, depending on its community, a new vertex attaches to certain nodes of Gn, but via m edges. So, when a vertex arrives, it attaches via m edges. In the paper of Jordan, and I, in fact, I showed that that we can take mkn a sequence of independent random variables such that if the community of V, so that if the community C of Vn plus 1 is K, is equal to K, then Vn plus 1 attaches to Vn via Nkn plus 1 edges. And the law of MKN for all n, the law of MKN for all n is pk, and the only assumption is that the only assumption in order to have a result is that pk as a second order moment. Okay. But for simplicity, we will assume that m is a fixed integer greater than 1, of course. And
so it's n or n?
M, sorry. And we can see that in this setting, multiple edges are permitted, but this is not a problem. And I forgot to say that each initial edge of the new vertex attaches independently from each other.
So its edge can be attached to different vertices?
Yeah.
But
not a problem.
Okay.
And now I need to explain how the communities modify the attachment probabilities. And in order to do so, let alpha be an affinity function from that maps a pair ij to a strictly positive number. I write a I j for this term. And I said affinity function because alpha ij represent the strength of attraction of type I on type j. And note that one may have a ij different from a j I, just like in real life, we never love exactly the same way we are loved. So we can have this asymmetry. So now we can define the geometric preferential attachment model. Definition: geometric preferential attachment. So suppose that Gn has already been constructed, and at time n plus 1, Vn plus 1 arrives, and we draw. So at time n plus 1, Vn plus 1 arrives. Okay, we draw its community according to mu. Okay, and then yes, let's V L n plus 1 be the else edge of V n plus 1. Then the probability that V L n plus 1 equal to V, where V is a vertex of Vn, given Fn, and given the community of Vn plus 1, okay, is equal to degree of V times the affinity, the alpha. In the first argument is the community of V, and the second, the community of V n plus 1. And we divide it by dn V n plus 1 in order to have a probability measured. dny is the sum over U in vertices in Gn, degree of U times alpha CU. Ouais, okay.
Can you say again why do you need alpha not to be alpha I j different from alpha ji in general?
No, it's just possible to have this assumption, but we can have.
Okay.
But we also can have an asymmetric function. Okay. We will not go into the details of the proof. It's a bit more difficult than for the preferential attachment, the historical preferential attachment model by Barabási and Albert. But by adapting the recurrence relations and using stochastic approximation theorems, we can roughly follow the same approach in order to obtain the limiting degree distribution. And in particular, this led us to apply the same lemma I introduced earlier. Okay.
Why is it called geometric? If there's some reason that.
Sorry?
Is there a reason why is it called geometric?
Yes, I will explain in a few. Okay. And in this setting, we can show that this theorem. There exists phi I depending only on the commutative. And in the more general setting, when the initial number of edges can be a random variable, phi A depends only on the expectation of the number of initial edges of a new vertex. But in the case where M is a fixed integer, phi I depends only on the communities. So okay, such that the proportion of vertices of degree D and of type I tends almost surely to a constant equal to mu I, so the expected number of vertices of type I in Gn times the sum of k over 1 plus g by I times the product from k to minus 1 g by I 1 plus g by I. Okay. Indeed, we can note that Jordan refers to this model as a geometric preferential attachment because the communities or types are viewed as points in a compact space, so as a spatial location, and the function alpha quantifies the difficulty of going from location I from location J, and it's a different perspective, but the underlying model is the same. Okay, and now we have an idea of what we call preferential attachment with communities. And for the rest of the presentation, I will focus on a preferential attachment model of the so-called sublinear type. And by sublinear,
before, so the function file that you're saying that it's existing, can you also construct that, or are you just saying in general, you know, that there is a function, but then I don't know, then what? And I mean, the function phi of I, you know, that you're saying that it's going to depend on your probability.
It is quite explicit, but we have to do the proof in order to identify.
Okay, so you know it. Okay, that was just the question. Okay.
For 3, sublinear. Preferential attachment model. By sublinear, I want to say that the probability that the new vertex attaches to V given Fn is given by the probability that Vn plus 1 attaches to V given Fn is equal to the degree of V at the gamma divided by the sum of the degree of U at the gamma, where gamma is a parameter between 0 and 1. And yes, I forgot to say that in order to focus on the core ideas, I am going back to the case without community, and I set n equal to 1. Okay, so n equal to 1.
Okay, M was the type.
M is the number of initial edge of a new vertex. So it is this case is we have trees.
Yeah.
Gn is a sequence of trees. Okay. Okay. When gamma equal to 0, it's called uniform attachment. When gamma equals to 1, we have already seen this case. So it is linear in the sense linear with respect to the degree, and when gamma is between 0 and 1 strictly, in fact, it's different. Apparently, it is almost the same model, but the exponent gamma actually changes many aspects, and we cannot carry out a proof analogous to the previous two proofs. This is mainly because the exponent gamma removes some linear properties that we had in the case gamma equal 1 or gamma equals 0. So in order to determine the limiting degree distribution, we have to find another way to describe the process, and in particular, to write the recurrence that allows to describe the proportion of vertices of each degree at time n. In this probability, we see that there is a dependence with respect to the entire degree distribution. This probability depends on the entire degree distribution, and I would say that the crucial point of the problem is to find a way to control the normalization term that we have in the probability when n goes to infinity. And since the attachment probability depends on the proportion of vertices of each degree, it is very natural to consider not only PDN, but the proportion of vertices of degree d in Gn, but rather the entire vector of the proportion. So we can define definition. Let Mn. Mn is a row vector from that maps n star to n, and Mnk is the number of vertices in Gn such that the degree of V is equal to K. So we want to obtain a recurrence relation for Mn, and not only for each coordinate of Mn. Okay. Now let's consider let y n plus 1.
Sorry, can I just ask, how is this Mn different from what you call the Qd of n?
It's the same thing, because Mnd is equal to Qd n.
Okay, so that's exactly the same option.
But I want a recursion for Mn and not just for each coordinate.
I see. Okay.
We'll see later why this is important, and we have a very interesting description of the process. So let y n plus 1 be a random variable taking values in random variable taking values in n star. I set E for the space, such that the probability that y n plus 1 is equal to I given Mn is equal to Mni I d gamma and we normalize in order to have a probability measure. Okay, and we set Mn plus 1 equal Mn plus R y n plus 1, where R is an infinite matrix. And R y is the row number y of the matrix R. And if we interpret this relation, we see that Mn plus 1 is obtained from by adding a random line of R in Mn. For instance, if yn plus 1 is equal to 1, so we add the first line, and we just add 1 to the second coordinate, which means that we have one more vertex of degree 2. And 0, in fact, is because we add one vertex of degree 1, but we because yn plus 1 is equal to 1, it means that vn plus 1 attaches to a leaf of Gn. So it attaches to a leaf. So the leaf in Gn plus 1 isn't a leaf anymore. So 0 is equal to 1 minus 1. If yn plus 1 is equal to 3, we add a new leaf, and then we remove a vertex of degree 3, and we add one vertex of degree 4. Okay. Okay, and for those who know, R is a replacement matrix, just like in classical Liouville processes. This is because the best way to follow the degree evolution is to treat Mn as a Liouville process. So I see the time, so I will skip a part about polyaion processes. Okay, I just want to say that that Mn is a measure-valued Polya processes. This framework has been developed notably by Cécile Mayer. Donc, Mn is a measure-valued Polya process. And so this framework of MVPP has been developed by Cécile Mayer, Jean-François Marquer, Denis Villemonet, and for this part of the talk, I mainly refer to a very interesting 2020 paper by Cécile Mayer and Denis Villemonet, titled "The Stochastic Approximation on Non-Compact Measure Spaces and Application to Measure-Valued Fourier Processes." And this framework essentially generalizes classical polynomials by allowing the number of colors to be infinite. More precisely, colors can take values in a Polish space E, and we allow to assign different weights to different colors. In our model, we have interpreted the degrees of nodes as colors. And this is time is over now.
Yeah, we still have a couple of minutes.
So, in fact, just in a few words, the interesting idea is that we can, if I set eta n equal to eta 0 is equal to 0, and eta n, it's eta n plus 1, it's eta n minus 1 plus delta yn. So this is and if I set eta tilde n, eta n over n, this is the mean of the number of the color that has been that have been drawn up to time n. So we can show that this quantity converges, and it's very interesting to see it, to understand why. So it converges. Okay. And as this number converges, then the proportion if we look at m tilde n, that is equal to mn divided by mn by the total number of vertices. So we can prove that mn tilde converges almost surely. And in fact, it is very interesting because we have some tools from Markov processes, but I don't have time to talk about it. Sorry.
Okay.
Thank you very much for your attention.
Okay. Yeah.
Question?
Yeah.
Yeah. So in the beginning, you said that these kind of this model applies to a lot of different kind of I don't know, phenomena, processes like social interaction, these things. What type of processes is suitable for this sublinear PA model? Is the normal one, or?
In fact, I don't know. Mathematically, it's very interesting. So, it appears in the literature. So, so I am interested in this model, but in fact, I don't know if it's more interesting to the modelization. So I don't know. but from a mathematical point of view, it's very, very interesting. Yeah. Because I did not have time to explain the rest of the proof, but there are very interesting tools in the proof.
But then, do you get a different behavior? Like you don't have the power law anymore, or you cannot compute that as?
Yes, because in fact, the limiting behavior is given by a quasi-stationary distribution of a Markov process, and in a more algebraic way, we can characterize this limiting distribution as if I set P the diagonal matrix such that the first in the first coordinate I put 1 and then 2 gamma. P allows us to have a weighted urn, and the limiting distribution depends on a left eigenvector for Q when Q is equal to R times P. So this matrix times this matrix of weight. And in fact, the limiting distribution depends on the nu, where nu is such that nu Q is equal to lambda nu, and nu, it's a probability measure over E. E is N star. So yes, we can compute it.
I see.
Lambda is the solution of something, and we can approximate it numerically, but it's not so explicit. It's the solution of an equation.
Any other questions also from Zoom, maybe? Okay, so if not, let's back Camille again. Okay, thanks a lot.